So this is really informal, just kind of like a primer to like what's the big deal about this guy? And so since you have a little bit of calculus, I want to kind of like talk about it. And relate it to a little bit simpler math, a little bit more algebra, since you haven't had vector calculus yet. But I think I can kind of tie this in, and I want to get the little history points right, too. So this right here, what's the significance? Okay, so this equation right here, basically, if you have a charged particle in a sphere, it tells us like that you just have like the electric field like emanating from that, and it doesn't go back in. Like it's just basically the flux of the electric field leaving this kind of bubble. Does that make sense? And you can use a little bit of calculus and come up with, by multiplying times charge, you can come up with, this is equivalent, this is obviously much simpler. We learned this earlier class. We have charge 1 times charge 2. You can actually derive this equation from this formula. Now I'm not going to do that because I'd have to use Gauss's law, and that's vector calculus. I'm not going to get into it, but that's basically, in a way, it's kind of stating this simpler formula. Does that make sense? It's just putting it in a way that makes it much more powerful. And I'll tell you the importance of this. And I'm not going to go through the derivation of the electromagnetic wave equation. This one is really simple. It just states that there's no such thing as a magnetic monopole. Now, what do I mean by monopole? That means like if you have a magnet, you always have to have north and south together. So if this is like a magnet, I got north and I got south, and if I have a bubble around it, you're going to have like little vectors coming out of the north side, but then they have to wrap back around and go into this side, so that this is called the divergence. The divergence here means like if you have a positive charge, they're going to like equal the charge within the sphere. That's basically what that ends up saying. This right here says that if you have a north, you're going to have a south. The divergence of this field is going to be 0. That means you got stuff coming in and stuff going out, and they have to equal each other. Does that make sense? So that's the no magnetic monopole. So this one right here is basically restating, like, so for Faraday and for Ampere, they came before Maxwell. And I can speak especially for Faraday. He was nowhere near as mathematically sophisticated as Maxwell. And Maxwell was like a mathematical genius. And like, it was really something else. And you probably already started picking that up from the film, right? So what this basically says, and this is Faraday's law, basically. And so Faraday's law in a simpler form is that the electromotive force around, so if I have a loop of wire and I have a magnetic field going through that loop of wire, that's a B field, right? If this magnetic field through this forms an area, do you get that? Like this little circle, it could be any shape, but in the most simplest case, this circle loop of wire forms an area that the magnetic field is passing through. Does that make sense? Okay. So the E field, or the electromotive force that's produced, is produced by the change of, let's go ahead and do the first derivative instead of the partial. The change of flux over the change in time. So it's the first time interval of the flux. Now what is the flux? What the flux? It is a scalar that's produced by a dot product between the area vector. So basically, if you have it would be the magnitude of the area and the direction of the area. And the direction of the area is perpendicular. It's a normal. So if I have a surface, like say I have a bubble, right? and I think about a little patch on the surface, and a surface is an area, right? So if it was a balloon, it'd be like me setting the marker on the surface of this balloon. Does that make sense? That would be the little vector that's associated with that area, and it's perpendicular to it. Does that make sense?
Yeah.
Okay. So that's a dot, and dotted with the magnetic field. So that's what the flux means. And so basically you can visualize it as like kind of arrows, like pointing of magnetic field kind of pointing through a surface. Even though it'd have to go in the surface on this side, it'd have to come out the surface somewhere. Does that make sense so far?
Yeah.
Okay. Now let me remind you what the dot product is. So if I have work scalar, it equals to force times, well, let's say since you know calculus, an infinitesimal amount of work is equal to a force that moves an infinitesimal distance. And these are vectors, and these are dot products. So that means when they're going in the same direction, you get work. But if they're perpendicular, you don't get any work. Does that make sense so far?
Yeah.
Okay, so if I take this and I plug this into this guy right here, that means if the flux is changing, and there's two ways you can change the flux. You can either, well, three ways, sorry. You can change the area, you can change their relationship as far as direction, so it can move, right? Or you can change the intensity of the magnetic field. And so this plays into the little Nearpod that you did, Ed puzzle that you did yesterday. That you learned that the changing magnetic field produces voltage, like in a loop of wire. You learned that yesterday, right?
Yeah.
Okay. So this has to do with the number of turns. So if you wrap this wire around multiple times, the voltage is going to increase like as an integral multiple of the loops around. That's all that N means. That means how quickly it happens. If it happens quick, you get a bigger voltage. Does that make sense?
Yeah.
Okay, so what are different ways you can change it? So what I can do with this loop of wire is flip it around, and that, you see that would change phi, because as it goes perpendicular or parallel, like if the loop is parallel to this magnetic field, then since the area vector would be pointing out of the board and the magnetic field going this way, this would turn to 0, right?
Okay, because they're perpendicular. Because you're saying because they'd be perpendicular.
Yeah, perpendicular, but we're talking about a dot product, not a cross product. What we were doing with the Lorentz force was a cross product.
Oh, okay.
Remember?
Yeah.
It was, the Lorentz force was force equals, which is a vector, equals Q, the velocity crossed with the magnetic field. This is a dot product. Notice this is not a vector, but these two things are. In a cross product, the result is a vector, and a dot product, the result is a scalar.
Okay.
Do you see that?
Yeah.
And it also, remember work, it's parallel, it's not 0, but if it's perpendicular,
It's 0.
It's 0.
Yeah.
So when if this loop like flipped like this to where the A vector was coming out of the board and the B is going this way, it would be 0.
Yeah.
So imagine if this thing is rotating around and around in a circle, the flux is going to go up and down, up and down. And it's even going to reverse sign because it'll be anti-parallel at some point. The vectors will be opposite directions. So that's how a generator works. You've got loops of wire that are turning round and round in a magnetic field to make voltage.
Oh, okay.
That's why these lights are on.
And it's happening really fast.
Yes.
Okay.
Yeah, in a hydroelectric dam, you basically have these giant coils of wire rotating, or giant magnets rotating around a stationary coil of wire to generate electricity.
Okay.
That's from Faraday's law.
Okay.
And again, this is the most generalized, well, not the most generalized, but a very generalized way to state this thing right here. That a changing magnetic field produces a voltage. And they knew this, Faraday knew this in 1832.
1830. Before, that's before Maxwell. Okay.
Yeah, that's before Maxwell. I mean, not before Maxwell existed, but before Maxwell did his important discovery.
Yes.
He did that during, I mean, he was in Scotland or England. He was in Britain, one of those.
Yeah.
Before the Civil War. So just to put it in historical perspective. Now, this part was also known. And basically, the first hint of this, and this Ampere came out with this in 1823, and this is basically based on what Ørsted discovered by running current, so if you have a battery and a loop of wire, and you put a compass here, the compass is gonna like go north and south based on the direction of the current. If you put on this side of the wire, the compass will flip around, because there's a magnetic field circulating around current flowing. Does that make sense?
Okay, so say that one more time.
Okay, so if you have a current flowing in the wire, so if I have positive conventional current flowing through this battery, I'm gonna have a magnetic field, like I could use the right-hand rule, and I'm gonna have the north on this side circulating around and south. So there will be a magnetic field wrapped around or circulating around this wire. Does that make sense?
Okay, yes.
All right, so that's basically what this part of it says. So this was already known. Faraday knew that if you change the magnetic field, that you can generate an electrical voltage, and that's induction. That's what you learned in that Ed puzzle. This you learned earlier, that a magnetic current in a wire produces a magnetic field. So that's not like anything new that Maxwell contributed. Now this basically means the current, and this is a vector though. It's kind of a vector form of current. So there's your current, there's a thing that's related to magnetism. And this right here basically says, this is called the curl. That's a cross product between this del operator, which is like a derivative, by the way.
Okay.
It's just a three-dimensional derivative. And the B field, the magnetic field, this is kind of, this basically tells you if you have a blob and you've got current going through it, that if you do a path integral around the blob, you're going to get a magnetic field circulating around it using Navier Stokes theorem.
Okay.
So that's Stokes theorem, that's vector calculus. Like I said, this is just kind of whet your appetite kind of thing, so I'm not going to get that deep into it. But what Maxwell noticed was like, what Maxwell noticed, I need a little bit more room here, so delete some of this stuff here.
Oh shoot, it hasn't been recording.
What do you mean?
Like the recording?
It wasn't recording?
No.
Are you serious?
No, I'm kidding. I'm kidding.
I'm putting this on the internet.
I'm kidding.
So the internet's gonna make fun of me. That's okay. I can take it. I've got thick skin. Okay, so there's that part. Okay, so what was Maxwell's genius? Okay, so there's a couple instances in the history of physics that people that were extremely mathematical kind of looked at stuff and saw these like kind of yin and yang kind of relationships, and just kind of with intuition understood that, hey, a piece is missing. Let me postulate it. Let me just kind of say, hey, what if I do this? What if I, because the physics, the actual experimentation had not caught up to that point. So this is kind of a revolution, because the way physics was done before Maxwell, I'm not aware of any other like really purely kind of mathematical or theoretical physicist, but Maxwell was one of those guys, and it's like he's kind of the first person to be like that. So basically what he says is like, okay, this connects magnetism, so a changing electric field causes magnetism. Now notice that this has no derivative, so this is not really dealing with change. This is kind of a static situation, right? So it's a current that's just flowing continuously produces this magnetic field circulating around the wire. That's what that's what this term says related to this. But what Maxwell's genius was this right here is relating a change in electric field also causes a magnetic field to circulate around. So that's kind of what that's saying right there. And so if you put these equations together with this term is necessary, you wind up with these equations producing a wave equation in space. Like, so saying, hey, there's a wave gonna exist here, and its speed, because the wave equation includes the velocity of the wave, was the speed of light. So what did he discover? And this was in 1865. This part came in 1861. But he synthesized all these equations into a wave equation in 1865, and basically said if you take an account and you put this piece in and you put all these together, that light is a what? An electromagnetic wave, and it travels at the speed of light. And he proved it mathematically before electromagnetic waves were even discovered, like explicitly.
Maxwell?
Maxwell, yeah. This was not experimentation. This is based on just playing around with the mathematics. It wasn't until Heinrich Hertz came along and did some experiments and showed that radio waves is what he discovered. They actually exist, and they have the. If you use these equations, you can find dead spots where the waves cancel out in a room, and Heinrich Hertz did that. And Heinrich Hertz was asked, "Is this useful?" And he basically said, "No." But it wasn't until Marconi invented the radio that like the whole thing took off, and now we have cell phones and all that stuff. Like this is huge.
That's crazy.
This is really mind blowing what he did.
So you said he found out that. Say
He
that one more time.
postulated this. He basically said to make these things balance out, because you got a changing B field, makes a potential difference around a circuit, like around a circle.
Mhm.
Now what this says is that a changing electric field causes a magnetic field to circulate around the electric field.
Dang.
And this was an intuition, as far as I know.
Like this was just like him just saying, like he just went at it. Like it was kind of with no, he just.
With intuition, yeah, like a
What?
gut feeling.
That's
my
crazy.
understanding of it.
That's crazy. How do you even do that?
He was a genius. Like he was a genius. And imagine like seeing this for the first time and putting this together and getting a wave equation out. And not only was it a wave equation, but it was an and Faraday already kind of had an intuition that light was an electromagnetic wave. He already had an intuition, but he didn't have the math chops to prove it.
So this is him just with math chops.
Yeah, this is Maxwell coming along like 30 years later and actually showing that it's true mathematically. And then, like I said, in 1888, it was Hertz that actually did the experiment and showed that, yep, there's waves out there. They're even a different frequency than light, and they behave in ways that follow these equations. By canceling out and finding dead spots in the room, they're called standing waves. Like all these different things. So he basically discovered radio, Hertz did, but he didn't discover the use for it. It was Marconi that actually put it to the wireless telegraph and made communications wireless communications. What you're holding in your hand right there is like the evolution of these things, these ideas.
Dang, Mr. Menes. Good explanation. Very good explanation.
Okay, so that worked then.